Hi and welcome back again. This is part 3 of the Unit 4 notes on atomic structure and history. We're still sticking with the same text, C6A. You're going to understand experimental design and conclusions used in the development of the modern atomic theory, including Dalton, Thomson, Rutherford, and Bohr's experiments. C3F, you will research and describe the history of chemistry and the contributions of scientists. And C6D, you're going to use isotopic composition to calculate average atomic mass of an element. If you remember last time we talked some about the electron, the discovery of the electron by the cathode ray experiment and finding out about the charge of the electron in the oil drop experiment. We are now going to tackle the proton, moving out of the cloud into the nucleus. First of all, a proton. Since those electrons have a negative charge, there has to be a positive charge somewhere in the electron in order for it to be electrically neutral. Okay, that positive charge is in the proton. Wilhelm Wien discovered the proton. Never have heard of this guy, but you know, it's in print, so it must be true. I don't know if that had to do with the canal ray experiments that we talked about, or if that was something else entirely different. Some facts about the proton. It is a positively charged particle. That's hard to say 5 times fast. It's found in the nucleus of the atom. It is much more massive than the electron. When you go to calculate the mass of an atom, these guys actually add up. They have a mass of... well, we actually invented a mass unit called the atomic mass unit to measure these, and they have the mass of 1 AMU. Just like with electrons, all protons are the same, whether it's a proton in a gold atom, a proton in a carbon atom, a proton in a uranium atom. A proton is a proton is a proton. Rutherford's experiment. Ernst Rutherford helped to discover the nucleus. He worked with Hans Geiger in Thomson's lab. If you remember, Thomson was the man famous for the plum pudding model of the atom. They were testing the validity of Thomson's model of the atom in a setup involving a sheet of gold foil, which we'll look at in more detail in just a couple slides. But he discovered that the nucleus is a very tiny part of the atom where the vast majority of the atom's mass is concentrated. Okay, it's not evenly distributed like Thomson's model would suggest, and instead it's located there in the center of the atom. Now, this is kind of putting the cart before the horse, but a neutron is also a particle located in the nucleus of an atom. It's identical to a proton, except that it has no charge. It's not negative or positive, although it has the mass of 1 AMU, very, very similar to the proton. However, whenever they started doing tests involving using a mass spectrometer to determine the masses of atoms, all of these atoms kept turning out roughly twice as heavy as they theoretically should have been. So scientists knew that there had to be something else accounting for the mass of the atom besides just the proton. And I already said all that. It was discovered by a scientist named James Chadwick in 1936. So it was the last of the 3 particles that we knew existed. Rutherford's model of the atom put a tiny nucleus with protons and neutrons at the center of the atom, and most of the rest of the atom is made up of empty space where electrons can be found. Now, at this point, they still didn't know much about the motion of electrons. They just knew that most of the mass was right there in the center where the protons and neutrons were, and the electrons had to be somewhere else. This is an interesting little statistic. If you were to put a marble in the center of the Houston Astrodome, then the rest of, if you were to keep the rest of the atom to scale, then the rest of the atom would fill the entire stadium. Okay, if you imagine a sphere that size, that's the size of the electron cloud that would be surrounding that tiny little marble-sized nucleus. The gold foil experiment. Rutherford and Geiger took a sheet of gold foil. They rolled it out very, very thin, only maybe around 1,000 atoms thick. They aimed alpha particles from a radioactive isotope. They aimed a beam of alpha particles at this sheet of gold foil. What they expected was for those particles to shoot straight through. Okay? Instead, what they found was that several of those alpha particles ended up bouncing back very, very wild directions from the line that they thought it was going to take. And it turns out that the only thing that would cause those to be reflected would be that large area of mass in the center of those atoms, with those particles running into it and then being bounced off in different directions. So this, gave them conclusive proof that there had to be unequal distribution of mass in an atom, hence most of the mass being concentrated in the nucleus of that atom. Okay? Based on the number of deflections, there were actually very few alpha particles out of the total that had been deflected. And they were able to calculate, based on the amount that were deflected and the angle they were deflected at, the relative size of that nucleus. We do a lab using marbles where we're going to be simulating this lab right here and showing how you can calculate the size of something without directly measuring it. And it's a lot of fun because you guys get to play with marbles. So here's the experiment. Here's your source of alpha particles shooting through a slit. This right here is a phosphorescent screen that glowed anytime a particle ran into it. Here's your gold foil. And as those particles came in, they would hit the gold foil. Several would pass through. A few would be slightly deflected. Very, very few are deflected back at very severe angles. And so most passed in between those nuclei. Not sure why my mouse is getting all floaty. That's weird. Most passed in between those nuclei, but a few would hit the nucleus, or be deflected by, or hit it straight on, and fly off in all sorts of strange directions. This proved that the atom's positive charge was concentrated in the nucleus. Again, just kind of recapping, a proton has an opposite but equal charge of an electron. Mass of a proton, if you're wanting some hard numbers, is a little more than 1,800 times the mass of an electron. Now, we're still talking a ridiculously tiny number. Remember back to our scientific notation. If something is 10 to the negative 24th, that means that we're talking 24 zeros before you get to the rest of the number. Okay, so very, very small. Mouse, you are really freaking out on me. So again, just kind of recap atomic structure. We saw this in the first video. You have neutrons in the nucleus with a mass equal to a proton but no charge. Protons, also fairly large in mass, but they've got a positive electric charge. Electrons orbiting with a negative electric charge equal to the positive charge in the proton, but the mass of the electron is so much smaller. Now here's the relationship, and this is big stuff. We talked some about atomic notation. In order to look at the notation you give an atom, you count up the number of protons. The number of protons is the atomic number. That's what determines what kind of element you have. If you're counting up the mass, though, you count both protons and neutrons, and the total mass that you get is the atomic mass. Okay, sometimes also called the atomic weight. This is not the same thing as the average atomic mass that you see on a periodic table. We'll talk more about that later. And you also look at the charges. If you've got an equal number of protons and electrons, then your total charge adds up to 0. If there are more electrons or fewer electrons, then that causes your atom to have a positive or a negative charge. Okay? And it becomes what's called an ion. Okay, so if you take a look in this, we've got some nuclear notation here. Sometimes you see the numbers on this side of the symbol, sometimes they're on the back side. This bottom number right here is your atomic number. That tells you that this helium atom, okay, He is helium, you look at the periodic table to tell that, has an atomic number of 2 protons, and it has a mass of 4. So if it's got 4 particles in its nucleus, 2 of those are protons, then how many neutrons would that have? Okay, time's up. So you take 4 minus 2, and that tells you that the other 2 particles have to be neutrons. Okay? And I think this is what I just said. So there you go. Obviously, I like that. I like that. Very cheeky. So, at this point I'd say any questions, but you guys are being awfully quiet, so I think we're going to call it quits right there.